1 millimeter, about the height of a grain of rice, and it is now the distance across which physicists can watch time run at 2 different speeds. In a laboratory in Colorado, there is a cloud of strontium atoms, and the ones at the bottom of that cloud are aging more slowly than the ones at the top, measurably, reproducibly, in print. That is Einstein, arriving on a bench. Now the people who built that clock want it 1,000 times better, and there is exactly one way to do it: entangle the atoms into a single quantum object. At which point the equation for what happens next asks you to name one time, and there is no longer one time inside that trap. There is no answer, not in quantum mechanics, not in general relativity, not in anything we have. The deepest unsolved problem in physics has quietly walked out of the black holes and onto a table in an ordinary room. So tonight, is this the breakthrough in modern physics we have been waiting for? By the end, you will know exactly where I land and why. Before we begin, if you enjoy questioning reality at this pace, a like or a subscribe really helps the channel grow. It is a small thing for you, but it means the world to me. Now, let's ease in. In the autumn of 1610, in the university town of Padua, a man stood beside a wooden tube a little over a meter long and refused to put his eye to it. His name was Cesare Cremonini. He held the chair of natural philosophy. He was one of the most respected thinkers in Italy, and he was being paid roughly twice the salary of the man standing next to him. The man standing next to him was Galileo Galilei, and the tube was pointed at Jupiter. Galileo had already looked. Earlier that year, he had published a short book describing what he had seen, and among the things he had seen were 4 small points of light beside Jupiter that moved from night to night, sometimes ahead of the planet, sometimes behind it, sometimes vanishing entirely for a few hours and then reappearing on the other side. They were moons. They were orbiting something that was not the Earth. And in a picture of the heavens where everything was supposed to turn around us, 4 small points of light that plainly did not, was a problem you could not argue away. So Galileo did the obvious thing. He invited his colleagues to look for themselves, and several of them said no. Cremonini said no. There is a letter from the period in which he explains that peering through those spectacles gives him a headache, and that he would rather not hear any more about the subject. Another Paduan philosopher, Giulio Libri, also declined, and then died later that same year, which prompted Galileo to remark, with the particular dryness of a man who has been arguing with someone for a long time, that having refused to see the moons of Jupiter from the Earth, Libri might perhaps catch sight of them on his way to heaven. It is very easy, from here, to laugh at this. It is one of the most quoted stories in the history of science, and it is nearly always told as a story about stupidity. Here is the evidence. Here is the instrument. Here is the man who would not look. But that is not what happened, and the real version is far more uncomfortable. Cremonini was not a fool, and he was not frightened of the moons. He was an Aristotelian, and he held a position that was, by the standards of his own framework, completely coherent. He believed that the heavens were a different kind of place from the earth, made of a different kind of substance, obeying different rules. And he believed something else, which is the part that matters. He believed that a device made of glass and brass, a device that had been demonstrated to distort and color and duplicate the things it showed you when you pointed it at objects on the ground, could not be trusted to report truthfully about a realm it was not designed for. He was not refusing a fact. He was refusing an instrument, on the grounds that the theory told him instruments of that kind were not the right sort of witness. And here is the thing that makes it worse. He had a point about the hardware. Galileo's telescope magnified about 20 times, which sounds impressive until you learn that its field of view was narrower than the full moon. Finding Jupiter in it at all was genuinely difficult. Holding it steady enough to track 4 points of light for an hour was genuinely difficult. The lens at the far end was no wider than a coin. The glass had bubbles in it, and the image at the edges swam. the headache was not entirely a lie. So what you actually have, in Padua, in 1610, is a serious man with a defensible philosophical position and a legitimate practical complaint, declining to use an awkward instrument to investigate a question his framework told him instruments could not investigate. Everything about his refusal is reasonable, from inside. He was still wrong. He was wrong in a way that took the rest of the century to fully undo, and the moons kept moving, whether or not anyone in Padua looked at them. There is a detail in this story that almost nobody mentions, and it sharpens the whole thing to a point. The year before Galileo published his book, in 1609, a German mathematician named Johannes Kepler had published a very difficult and very unpopular work in which he showed that the planets do not move in circles, they move in ellipses. The perfect circular machinery that everybody had been maintaining for 1400 years was not needed. The answer was already in print. It was sitting in libraries, unread, while the philosophers of Padua debated whether it was proper to look through a tube. The knowledge was available, the instrument was available, and the community that most needed both was busy with something else. Now I want you to hold that scene, because we are going to leave 1610 almost immediately, and we are not coming back to it for a long time. But it is going to be underneath everything else in this video, the way a low note holds under a piece of music. And near the end we are going to walk straight back into it from a completely different direction, and you are going to find that the room looks different. Because the story I actually want to tell you tonight is about a problem in modern physics that has not moved in 110 years. It is the biggest unsolved problem there is. It has swallowed the careers of some of the most capable people who have ever lived, and it has generated some of the most beautiful mathematics human beings have ever produced, and it is, by any honest accounting, exactly where it was when it started. And there is a physicist, working right now, who thinks she knows why. Her argument is not that everyone else is stupid. Her argument is not that the mathematics is wrong. Her argument is that for 110 years, we have been trying to solve this problem the way you solve a problem when you have no way of checking your answer, and that this is a specific and recognizable failure mode with a specific and recognizable cure. The cure is not a better theory. The cure is a telescope. And her claim, which is either the most important thing happening in fundamental physics or a very expensive detour, is that the telescope already exists. It is sitting in laboratories right now. It has been built for other reasons, by other people, in pieces, and almost nobody in the field that needs it is looking through it. Let me show you what the problem is first. Then I will show you the instrument. Physics has two theories that work. That sentence is doing a lot of quiet work, so let me unpack it. It does not mean physics has two theories that seem plausible, or two theories that have survived some testing. It means physics has two descriptions of the world that have been checked, adversarially, by people who wanted to break them, to a level of agreement that has no parallel anywhere else in human knowledge. General relativity tells you that gravity is not a force pulling on things, but the shape of space-time itself, and that mass and energy bend that shape. It predicted the precise drift of Mercury's orbit that had been bothering astronomers for 60 years. It predicted that starlight would bend around the sun by a specific angle. It predicted that clocks would run at different rates at different heights, which is why the satellites over your head have to correct their timekeeping by about 38 microseconds every day, and why your phone would put you in the wrong city by lunchtime if they did not. In 2015, it predicted the exact waveform of two black holes spiraling into each other more than 1 billion light-years away, and a pair of instruments in Louisiana and Washington state recorded that waveform, and it matched. Quantum mechanics tells you that at small scales, the world is not made of little objects with definite properties, but of amplitudes that interfere, and that what you get when you measure something is a probability rather than a certainty. It is the reason your phone has a processor in it. It is the reason lasers exist, and magnetic resonance imaging, and light-emitting diodes, and every solid-state device you have ever owned. And in its most refined form, quantum electrodynamics, it predicts a particular property of the electron that has now been measured to about 1 part in a million. 12 decimal places of agreement between a calculation and a laboratory. 2 theories, both of them extraordinary, and they contradict each other. Now, people say that a lot on the internet, usually without saying how. So let me be specific, because the specific version is what the rest of this video is built on. The contradiction is about time. In quantum mechanics, time is absolute. The central equation of the theory, the Schrödinger equation, has time in it as an external parameter, a thing that ticks along in the background at the same rate for everybody, regardless of where they are or how they are moving. Space, meanwhile, is treated completely differently. The equation has 1 derivative with respect to time, and 2 with respect to space, and position becomes an operator, a mathematical object of an entirely different type. Time is the stage. Space is what happens on it. And underneath the whole structure sit the transformations of ordinary pre-relativistic physics, the ones that assume everyone's clock agrees. In general relativity, none of that is true. Time and length are not absolute. They depend on how you are moving and where you are standing. The transformations underneath the theory are the ones Einstein wrote down in 1905, and the single most radical thing about them is that they mix space and time together. They do not treat them as separate quantities that happen to be related. They treat them as 2 aspects of one 4-dimensional object, and the equations have to be second order in both, because you cannot treat one as a stage and the other as a play if they are the same material. And once you add mass, so that space-time is curved, the rate at which time passes becomes a thing that varies from point to point. There is no universal now, there is no background tick. So one theory needs a single clock for the whole universe, and the other theory says there is no such clock. That is the crack. Everything else is downstream of it. And here is the shape the last 110 years have taken. It is a shape you will recognize from a fairground. You know the game. A hole opens, a mole comes up, you hit it with a mallet, and while you are hitting it, another hole opens somewhere else. Einstein himself played this game for a decade. He had his idea in 1907, the one he later called the happiest thought of his life, that a person in free fall does not feel their own weight, and therefore acceleration and gravity are somehow the same thing. Beautiful. Now make it work. He tried encoding gravity as a simple scalar field, 1 number at every point, and the scalar field would not carry it. Hole opens. He tried a version in which the speed of light varies from place to place, which caused problems of its own. Hit it down. He wondered whether it had been a mistake to unite space and time in the first place. Hit that down. And eventually, after 8 years and a great deal of assistance with the mathematics, he reached for tensors, a different and much more complicated kind of object, and the moles stopped coming up, and the result was general relativity. That is the game played well. The mallet was the right response, and the theory that came out the other end has never failed a test. But watch the same game played on the unification problem, where nobody has ever been able to check the answer. The most developed attempt is string theory. The idea underneath it is genuinely lovely, and I want to give it its due, because it is far too easy to be glib about this. The proposal is that the point-like particles of the standard model are not points at all, but tiny extended objects, and that the different particles we see are different modes of vibration of the same kind of object, the way one violin string gives you different notes. Unify the particle zoo the way a single string unifies a scale. Anyone who tells you that is not an elegant idea has not understood the idea. Then the moles start. For the original version to be mathematically consistent, space-time has to have 26 dimensions, and the theory contains only force-carrying particles, with no matter in it at all. That is 2 moles at once. Solution: introduce a new symmetry, called supersymmetry, which brings in matter particles and drops the dimension count from 26 to 10. Hit them down. New hole. There is now more than one consistent theory. There are 5 of them. Solution: show that the 5 are different faces of a single 11-dimensional structure. Hit it down. New hole. The theory has an enormous number of possible ground states, possible ways of curling up the extra dimensions, and each one gives a different set of physical constants. How many? The figure usually quoted is 10 to the 500, which is not a census. Nobody has counted them, but an order of magnitude estimate, and it is a number so large that it is difficult to attach meaning to. And if your theory can produce almost any universe, it has stopped predicting this one. 58 years. Enormous mathematical achievement. Genuine physical insight along the way. 0 confirmed predictions. I am not telling you this to sneer at string theory. I am telling you because of the shape. Every single one of those moves is a mallet swing, and the reason people kept swinging is that there was nothing else to do. There was no measurement coming back. There was no experiment saying you have gone wrong here, try again from the 3rd step. In a field with data, wrong turns get corrected within a few years because reality objects. In a field without data, wrong turns compound quietly for decades, and the only feedback available is whether other theorists find your move interesting. That is not a moral failing. That is what happens to any intelligent system when you cut the feedback. And it raises a question that we will need before we can go any further. When you have been swinging a mallet for 100 years, how do you tell whether you are nearly finished or whether you have been defending a shape that was never there? There is a physicist named Ivette Fuentes who, when she was a student, looked at string theory and thought, "This reminds me of the Epicycles." I want to spend a little time on why that sentence is more damning than it sounds. Because the epicycle story is one of the most misused analogies in all of popular science, and the version most people carry around is wrong in a way that actually weakens the point. The true version is sharper. Start with the problem the ancients were trying to solve. You watch the sky for a few years, and you notice that most of what is up there behaves itself. The stars turn together in a single sheet. The sun crawls along a fixed path. The moon does something regular. And then there are 5 points of light that do not behave at all. They drift eastward against the stars for months, and then they slow and stop and go backwards for a few weeks, and then stop again and resume. The Greeks called them the wanderers. We call them planets, which is the same word. Now, if you want to describe that motion, you need a shape to describe it with. And here, the ancients made a decision that governed astronomy for the next 1400 years. They decided that the shape had to be a circle, not because the data said so, because the circle was perfect. It was the figure with no beginning and no end, the figure every point of which is equally far from the center, and the heavens were the perfect region of the cosmos, and therefore heavenly motion had to be built from perfect figures, moving at constant speed. That was not an observation. It was a commitment about what kind of answer would be acceptable, made before anyone looked closely. And a single circle does not fit. So you put a small circle on the rim of the big circle and let the planet ride the small one, while the small one rides the big one, an epicycle on a deferent, and now you can produce a loop, and the backwards motion appears. Better. Still not right. So you move the center of the big circle slightly off the Earth. Better. Still not right. So you introduce a point that is not the center, off on the other side, about which the motion is required to look uniform, even though it is not uniform about the center. A device called the equant, which is frankly a fudge, and which was recognized as a fudge at the time. Here is where the myth comes in. You will very often hear that this system eventually needed 600 circles, or 80 circles, or that it collapsed under its own absurd complexity. It did not. Ptolemy's system, as written down in the 2nd century, uses something like 40 circles in total. And when Copernicus put the sun at the center, 1300 years later, his model was not simpler. He got rid of the equant, which he hated on philosophical grounds, and paid for it with more circles. There is also a famous quip attributed to King Alfonso X of Castile, to the effect that had he been present at the creation, he could have offered some useful advice on simplifying the design. He almost certainly never said it. It appears centuries after his death. So the popular story is wrong, and correcting it does not rescue the epicycles. It makes the indictment worse. Because if the system had genuinely collapsed under 600 wheels, then the lesson would be a lesson about complexity, and complexity is easy to notice. You would simply say, when your model gets too baroque, something is wrong. That is a comfortable lesson. It gives you a warning light. But that is not what happened. What happened is that a moderately complicated model, with about 40 circles, worked. It made predictions. It was used for navigation, and for calendars, and for casting horoscopes, and it was accurate enough for all of those purposes for 14 centuries. Nobody was forced to abandon it by a crisis. It just quietly required, forever, a set of components that had no reason to be there except that somebody had decided in advance what shape the answer would take. And then, in 1609, Johannes Kepler spent years fighting the orbit of Mars, the worst behaved of them all, the one where the discrepancies were largest, and did something that took extraordinary nerve. He gave up the circle. He tried an oval. He tried the wrong oval for a long time, and eventually he found that if you allow the orbit to be an ellipse, with the sun sitting not at the center, but at one of two special points called the foci, and if you allow the planet to speed up when it is closer and slow down when it is further away, then everything falls into place at once. No epicycles, no equant, no deferent, one curve, one rule, and the wandering stops being a puzzle and starts being a consequence. 40 pieces of machinery, gone in a single move, not because someone calculated harder, because someone stopped insisting on the shape. That is what Fuentes saw when she looked at the dimension count, and the supersymmetry, and the 5 theories folded into one, and the landscape of possible vacua. Not that the work was bad, that the work had the texture of machinery being added to preserve something nobody had checked. And if you want to know what our perfect figure might be, there is an obvious candidate sitting in plain sight, and it is so deeply built into how the problem is stated that it is almost invisible. We say quantum gravity. We say we need to quantize gravity. Think about what that phrase assumes. It assumes that gravity is a force like the other three, and that the correct thing to do with it is what we did to electromagnetism in the 1940s. Take a classical field, apply a known procedure, get a quantum field theory with a force-carrying particle. That procedure worked 3 times in a row. It gave us quantum electrodynamics, and then the theory of the strong force, and then the electro-weak theory. 3 for 3. Of course you would try it a 4th time, and it fails. It fails in a technical way that was pinned down precisely in 1986, when 2 physicists showed that if you carry the standard calculation for gravity to the 2nd level of correction, the infinities that appear cannot be absorbed the way they are absorbed in the other theories. The procedure that worked 3 times does not work here. Roger Penrose has been asking, for decades, whether we have the question backwards. He puts it as a choice. Should we quantize gravity, keep quantum theory as it stands, and modify general relativity to fit it? Or should we gravitize quantum theory, keep the principles of general relativity, and modify quantum mechanics instead? Almost the entire field has taken the first road. Penrose argues for the second, and his reason is worth hearing. Quantum theory has an unsolved problem of its own, the measurement problem, the question of why we never see the superpositions the equations permit. A modification that fixes the unification problem and the measurement problem at once is worth more than a modification that fixes neither. Fuentes' own position is that both theories will probably have to bend, but she agrees with Penrose about the priority, and she agrees for a reason that is grounded in something specific rather than in taste. Gravity is the only interaction with an equivalence principle. Sit in a sealed box with no windows. If you feel yourself pressed to the floor, there is no experiment you can perform inside that box to determine whether you are sitting on a planet or being accelerated through empty space. That is not a curiosity. That is the founding observation of general relativity, and nothing like it exists for electromagnetism, or the strong force, or the weak force. There is no sealed box in which you cannot tell an electric field from an acceleration. So there is at least a hint, written into the structure of the thing, that gravity is not the fourth member of a set, and if it is not, then the procedure that worked 3 times was never going to work a fourth, and the last 50 years of increasingly ornate machinery has been epicycles. That is a diagnosis. It is not a cure. And a diagnosis without a cure is just a more articulate way of being stuck. So how does anybody get unstuck? To answer that, I have to tell you about a student in a cafeteria in Mexico City. Every so often, a whole line of scientific work turns out to have started with somebody saying no to something reasonable, and this is one of those. At the National Autonomous University of Mexico, in the middle of the 1990s, there was a professor named Luis de la Peña who taught quantum mechanics in a way that his students remembered. Most courses on the subject do something specific. They teach you the machinery, and they root carefully around the question of what the machinery means. You learn to write the equation, you learn to solve it, you learn which quantity to square to get a probability, and if you ask what is actually happening, you are told, gently, that this is not the productive question, and that people have made careers out of getting lost in it. De la Peña did the opposite. He taught the interpretations. He talked about what the theory might be saying about the world, and he did it in front of undergraduates, which is not the safe choice. And one of the undergraduates listening was a young woman named Ivette Fuentes, who found the whole thing electrifying, and who went to him at some point and said, in effect, "I want to work on this with you." He said no. Not dismissively. He told her the truth, which was that he had spent his working life in the foundations of quantum mechanics and had found it a punishing road, and that he did not want that for her. "Go and do something more mainstream," he said. "And if you are still interested when you are grown up, come back." He knew what he was talking about. De la Peña had spent decades on a program called stochastic electrodynamics, which is an attempt to derive the strange behavior of quantum systems from the idea that empty space is filled with a real, fluctuating electromagnetic background that particles are constantly being buffeted by. Whether or not you think that program succeeds, and most physicists do not, it is a serious attempt to answer the question rather than to root around it. And it is exactly the sort of work that leaves you a respected figure at your own university and a marginal one everywhere else. He had lived the cost of the choice he was being asked to endorse. I want to stay here for a moment, because this is one of the quietly extraordinary things a teacher can do, and it is almost invisible if you read past it. He had in front of him a first-rate student who wanted to work on the thing he cared about most. Every incentive in academic life pointed towards saying yes. Instead, he told her what it had cost him, and sent her away from it. That is not discouragement. That is somebody weighing his own preference against her whole career and choosing hers, and it looks exactly like a rejection from the outside. And here is what makes it more than a nice anecdote. If he had said yes, she would have become a foundations theorist. She would have spent 30 years in the same seminar rooms as everyone else, working on the same problem with the same tools. Instead, because he said no, she went into quantum optics, the branch of physics that was about to learn how to build things. And that is the entire reason that, 25 years later, she is one of very few people working on the unification problem who knows how to design an apparatus. A kindness redirected her into the one position from which the problem might actually be attackable, and neither of them could possibly have known that at the time. The story does not end there, though, because there is a second no in it, and the second one is hers. She went back to De La Peña at the end of her degree because she wanted a letter of recommendation. There was a competition to spend a summer at Fermilab, and she wanted to enter it. He asked her, not unkindly, why he should write her a letter. She said, "Because I got the top grade in all your classes." He said, "Many students do that." And then they simply started talking, and she told him what she had been thinking about, which was that all of her classmates who wanted to do theory were going into string theory. She had been fascinated by it herself, genuinely fascinated. The idea that particles are not points but vibrating strings, and that the whole variety of matter is one object singing different notes, is beautiful, and she says so. But the further into it she got, the more the dimension counts, and the added structures started to look like something else. And eventually, she said out loud the thing we spent the last part on. "This reminds me of the Epicycles. It cannot be right." He smiled, she says, and told her he would write the letter for wherever she wanted to go. That is what changed his mind, not the grades, the fact that she was prepared to say a critical thing about the direction everybody else in her cohort was walking in, and to say it as a 22-year-old with nothing at all to stand on. Now, she had already made one significant choice before this, and it is the third refusal in the sequence. Like a great many physics students, she had fallen in love with astronomy along the way, and she did her undergraduate thesis on a class of galaxies called Seyfert galaxies. These were catalogued in 1943 by an astronomer named Carl Seyfert, who noticed that a handful of spiral galaxies had cores so bright and so compact that they looked almost like single stars, and whose light carried the signature of gas moving at thousands of kilometers per second. What he had found, though it took another 30 years to understand, was a galaxy whose central black hole is actively feeding, pulling in material, heating it to the point where the core outshines the 100 billion stars around it. Her question was a good one, whether the presence of a companion galaxy nearby can disturb a galaxy's gas enough to send material tumbling inward and switch the center on. This is a real and still open problem, and the way you attack it is statistical. You take a large sample of galaxies with active cores and a matched sample without, and you count companions, and you look for an excess. It went well. Her first published paper came out of it, and it was a letter, which in astronomy means the journal thought it was worth publishing quickly. And she stopped, not because it was going badly, because it was going well, and she could see the rest of it. She could see a whole life spent on those objects. And she says, it would probably have been a lot of fun. But she noticed something that took her a long time to be able to state clearly, which was that no possible answer to any of those questions was going to tell her what she actually wanted to know. Suppose you get the perfect result. Suppose you determine exactly what triggers the accretion. You will know something true and interesting about a class of objects. You will not be one step closer to knowing what reality is made of. That is a very unusual thing to be able to notice about your own success, and an even more unusual thing to act on. So, no to foundations, from a teacher who was protecting her. No to string theory, at an age when saying no to string theory cost you your peer group. No to astrophysics, at the exact moment astrophysics started working for her. 3 refusals, and none of them came with an alternative attached. She did not know where she was going. She only knew what she was walking away from, which is a much harder position to hold than people who tell inspiring stories about scientists usually admit. Walking towards something is sustaining. Walking away from 3 things in a row, with no destination, is mostly just frightening. And then, in 1997, somebody ran into a cafeteria. She was sitting in the university cafeteria, doing homework when a colleague of hers named Pablo Barberis came running in and said, "They have demonstrated quantum teleportation." That was December of 1997, and what he was talking about was an experiment in Innsbruck, in the group of Anton Zeilinger, who would eventually share a Nobel Prize for this line of work. The name is unhelpful, so let me say what actually happened. Nothing was transported. What was transferred was a quantum state, the complete description of one photon, including the parts of it that cannot be measured without destroying them, moved onto a different photon somewhere else, using entanglement as the channel, and a couple of ordinary bits of classical information to complete the operation. The original state is destroyed in the process. Nothing travels faster than light. And it is still one of the strangest things anybody has ever done in a laboratory, because it means the full quantum description of a system is a transferable object. And her colleague told her something else, in the same breath, which mattered even more to her. They can now trap single atoms, single particles, held one at a time in an ion trap or in an optical cavity, addressed individually. Here is why that landed the way it did. Her teacher, De la Peña, used to say something in class that had lodged in her. Quantum mechanics is a theory that does not apply to single particles. He did not mean the equations break. He meant that every experiment anyone had ever done had been done on ensembles, enormous numbers of atoms at once, so that what you measured was always a statistical average, always a smear over many systems. If you want to argue about what a quantum state actually is, and someone points out that you have only ever observed a crowd, the argument stops there. So when she heard that people could now hold one atom and watch it and do things to it, she made a prediction about her own future, and she was right. That area, she thought, is about to become extremely interesting, because for the first time we will be able to put the foundational questions to an actual apparatus. She went to Imperial College in London to do quantum optics, in the group of Peter Knight. When she arrived, everyone there was working on quantum information and entanglement measures, so her doctorate ended up sitting on the boundary between the two, the physics of light and the mathematics of what entanglement is and how much of it a system has. It went well, and from there she went to the Perimeter Institute in Canada. You should picture the Perimeter Institute as it was then, rather than as it is now. Today, it is a striking black building with a reputation. When she got there, it was the old post office in Waterloo, with sofas and a bar and a blackboard, and she was, she thinks, the first or second postdoctoral researcher hired to do quantum information. That was the entire quantum information effort. Down the corridor were the string theorists and the quantum gravity people and the foundations group, and they were the establishment of the building. And she started attending their seminars, and she got jealous. That is her word, and I like it, because it is honest in a way that people usually are not about their own careers. She would sit in talks about general relativity and quantum field theory in curved spacetime and think, I am missing out on something. Meanwhile, back in her own field, the conversation was largely about quantum cryptography, which is a beautiful idea, using the impossibility of copying a quantum state to build a communication channel that cannot be eavesdropped on. But when you actually work on it, the day-to-day shape of the job turns out to be finding an attack, patching the attack, finding the next attack. She looked at that and thought, this is the same game again. It is whack-a-mole, running inside a healthy experimental field, and I will get lost in it. So she considered switching to general relativity outright, and then ran into a problem that anyone who has changed direction will recognize. She had already jumped. She had a paper in astrophysics, a doctorate in quantum optics, and a paper in quantum information. Jumping a fourth time, in her early 30s, was not obviously a survivable career move. What she did instead was the thing that made her. She did not choose one of them. She mixed them. She took the mathematics of entanglement measures, which she had learned at Imperial for quantum information purposes, and she applied it to quantum field theory in curved spacetime, asking what happens to the entanglement between two particles when one of the observers is accelerating or falling towards a black hole. The paper is called Alice Falls into a Black Hole: Entanglement in Non-Inertial Frames. It came out in 2005. It is still her most cited work, and it effectively opened a field. There is now a recognized research area called relativistic quantum information, and that paper is near the root of it. The result inside it is the sort of thing that rearranges your assumptions quietly. Take two particles that are perfectly entangled, hand one to an observer who stays still, and one to an observer who accelerates, and the entanglement between them degrades. Not because anything measured them, not because they interacted with anything, simply because an accelerating observer does not agree with a stationary one about what counts as empty space. The vacuum for one of them is a warm bath of particles for the other, and that disagreement eats the correlation. Push the acceleration high enough, and the entanglement is gone entirely. Entanglement, which everybody had been treating as a fixed resource, turns out to be a quantity that depends on how you are moving. And then, having done that, she looked at what she had built and identified the problem with it. It was all completely untestable. She could write down, precisely, what happens to entanglement near the horizon of an eternal black hole. Nobody was ever going to check. There is no measurement you can make inside a black hole. There is no measurement you can make near one. The whole beautiful structure was a set of statements about a regime that would never talk back, and she had come out of quantum optics, where the loop between proposal and result runs continuously, where you write a paper suggesting a sensor, and an experimental group picks it up, and 18 months later, somebody has built the thing. She had lived inside a field with feedback and then walked into a field without it, and she could feel the difference in her hands. She has a phrase for what was happening to her at that point. I still felt that I was getting lost in maths, and getting lost in maths. So she decided to do something about it, without having any idea how. She hired a postdoctoral researcher named Carlos Sabin, a theorist, but a theorist who worked close to experiments on superconducting circuits, for no better reason than that she knew the direction she wanted to travel. She did not have a plan, she had a heading, and the two of them started trying to combine quantum metrology, which is the science of measuring things as precisely as quantum mechanics allows, with quantum field theory in curved spacetime. It is worth pausing on what quantum metrology is, because it is the hinge of everything that follows. When you measure something, you are really asking how much a signal changes the state of your probe, and how well you can tell that change from noise. Quantum metrology is the discipline of working out the absolute flaw on that question, the best any measurement could possibly do, given the laws of physics rather than the quality of your engineering, and then designing states of matter and light that reach it. It is the reason a modern atomic clock is not simply an old clock built more carefully. And what she was proposing was to take that discipline, which had been developed to measure magnetic fields and rotations and time, and point it at the curvature of space-time. That combination is the whole of the rest of this video. But before I show you what came out of it, I need to tell you what she thinks the actual disease is, because she has a diagnosis, and it is not about mathematics at all. Imagine people sitting around a fire, a very long time ago, looking up. There are points of light overhead, and they have no idea what they are. They have no instrument of any kind. The only apparatus available to them is the pair of eyes in their heads, and with that apparatus, they are going to try to work out what the world is and where they are inside it. You can guess how well that goes. You get beautiful stories. You get careful, patient, entirely serious accounts of the heavens that are wrong in every particular, and they are not wrong because the people were unintelligent. They are wrong because there was no way, using eyes alone, to be right. Then somebody grinds a piece of glass, and everything changes. Not because the telescope answers the questions, because the telescope makes the questions answerable. You point it upward and you find moons around Jupiter and phases on Venus. And eventually, with better glass, you find that the faint smudges are other galaxies, and that they are moving away from us, and that they were closer together in the past. Every large idea in cosmology is downstream of somebody building a better instrument and then having to explain what came out of it. The same story runs in the other direction, towards the small. The Greeks reasoned their way to atoms, the argument that you cannot keep dividing matter forever, that there must be some unit that resists further cutting. It is a fine argument, and it is nearly 2,500 years old, and for almost all of that time, it stayed exactly where it started, because there was no way to check it. Then people started building instruments that could touch the scale, and the atom stopped being a philosophical position and started being an object with a size and a structure and a set of properties you could get wrong. And notice how that went, because the shape of it is the point. First you get an idea from intuition, from philosophy, from creativity. There must be an indivisible unit. Then you cast that idea into ordinary language carefully enough to say what you mean. Then you cast it into mathematics, because mathematics is what lets you say something precise enough to be tested. Then, and this is the crucial step, that mathematics is specific enough to tell you what apparatus to build. So you build it. And then it gives you a signal, and the signal does not match, and you go back and fix the theory, and the fixed theory tells you how to improve the apparatus, and around you go again. That is the loop, and you can watch it running through the history of atomic physics like a heartbeat. The idea of the atom as a featureless little ball. Then a model where the atom is a positively charged pudding with electrons stuck in it like raisins. Then somebody fires alpha particles at a sheet of gold foil, and a few of them bounce straight back, which cannot happen if the atom is a pudding, and out of that comes a model with a hard, tiny, dense nucleus and electrons around it. Then that model turns out to be unstable. The electrons should spiral in within a fraction of a second, and out of the repair comes quantum mechanics itself. Every single step was forced. Not one of those revisions was a matter of taste. Reality objected, in a laboratory, and somebody had to accommodate it. Here is the essential thing about the loop, and it is easy to miss because it sounds like a technicality. You cannot build an apparatus without a theory. There is no such thing as looking at nature without a hypothesis. You would not know where to point the instrument or what to record. So the theory has to come first, and the theory will very often be wrong. That is fine. That is what it is for. A wrong theory that is specific enough to specify a machine is worth infinitely more than a right theory that specifies nothing, because the wrong one gets corrected and the vague one just persists. Quantum optics has this loop running at full speed and has done for 30 years. Somebody has an idea for a sensor. They write it up as a proposal. Here is the mathematical model. Here is the measurement you make. Here is the precision you should get. An experimental group reads it and thinks that looks feasible. They collaborate. 18 months, 2 years, sometimes 5, and the thing exists, and it either performs as predicted or it does not. And either way, everybody learns something. This is why quantum technology has moved so fast. It is not that the people are cleverer, it is that the loop is closed. Now bring that back to the problem we started with. At the scales where quantum mechanics and general relativity actually interfere with each other, how many times has that loop closed? Almost never. In 110 years there are a handful of instances, and they are precious enough that people who work in the area can list them. Here is one, and it is worth telling because it shows what health looks like. A physicist named Tim Ralph proposed an extension of quantum field theory in curved spacetime that took into account the possibility of closed time-like curves, paths through spacetime that return to their own past. That sounds like the sort of thing that could never touch an experiment. But he was careful enough to derive a consequence you could actually look for, and he wrote it up as a proposal. A consortium of theorists and experimentalists looked at it. The theorists found it interesting. The experimentalists, more importantly, found it feasible. They ran it, and they found no evidence for the new theory. That is not a disappointment. That is the loop closing. Somebody had an idea, made it precise, made it specific enough to specify an apparatus, and nature said no. Notice how ordinary that sounds. And then notice that in unification research, it is close to unheard of. So what do you do in a field where you cannot look? You do the only thing available. You use the tool you are strongest with, and the tool physics is strongest with is mathematics. You build enormously sophisticated structures out of pure formal reasoning, because that is what you have. And I want to be scrupulous here, because it would be very easy to be unfair. String theory, loop quantum gravity, the whole apparatus of modern theoretical physics. These are not failures of nerve. They are what a highly capable field does when it is blindfolded. They have produced genuine mathematical discoveries. Whole areas of pure mathematics have been reshaped by physicists chasing consistency conditions in theories nobody can test. But mathematics has a property that becomes dangerous in the absence of data. You can build many theories. You can build almost as many as you can imagine. Two people can construct rival frameworks that are both internally consistent, both beautiful, and that make contradictory predictions about the world. And there is nothing inside the mathematics that will tell you which of them nature chose. Elegance is not a tiebreaker. It feels like one, and it is not. To break the tie, you have to go outside, to the instrument. And Fuentes' summary of where the field stands is the sentence I want you to carry through the rest of this video, because we are going to come back to it twice. At the scales where quantum mechanics and general relativity meet, she says, we are blind. We do not have a poor instrument. We do not even have our eyes. Sit with the shape of that for a second, because it is not a complaint about funding, and it is not a complaint about cleverness. It is a claim that the single most important input to scientific progress has been missing from this problem for its entire existence, and that everything strange about the last century of unification research, the length of it, the ornateness of it, the way whole programs can persist for 50 years without ever being wrong about anything, follows from that one absence. And if that is the diagnosis, then the cure is obvious, and it is not a smarter theory, it is an instrument, which raises the only question that matters. Is one possible? For a long time the answer was assumed to be no, on the grounds that the effects live at scales so absurdly small that nothing could ever reach them. That assumption is the thing that turns out to be wrong, and the evidence has been accumulating in plain sight for about 25 years. Every physics student is taught the same division of territory, usually in the first year, usually as a throwaway line. Quantum mechanics applies to the very small, atoms, electrons, molecules. Down there, where things are tiny, the world goes strange. General relativity applies to the very large. Planets, stars, galaxies, the universe as a whole. Out there, where things are heavy, spacetime bends. In between, in the world you live in, ordinary physics works fine, and neither strangeness troubles you. It is a useful thing to tell a 19-year-old. It is also, at this point, comprehensively false, and the falseness has been accumulating in laboratories for a quarter of a century, without ever quite being absorbed into how the unification problem gets framed. Start with the quantum side. In 1997, when Anton Zeilinger's group demonstrated teleportation, the entire experiment sat on a table. Mirrors, lasers, crystals. A room you could walk around. That is the scale at which quantum phenomena were supposed to live. Then Zeilinger asked a simple question. How far apart can we pull this before it breaks? In 2004, his group ran entanglement and teleportation between two buildings in Vienna, through about 600 meters of optical fiber laid under the Danube, through a working sewer, as it happens, which is the kind of detail that gets left out of the textbooks. 600 meters, still fine. Then they left the fiber behind entirely. In 2007, they set up on La Palma, in the Canary Islands, and pointed a beam across 144 kilometers of open Atlantic air at a receiving station on Tenerife. Not through a cable, through weather, through 144 kilometers of atmosphere with turbulence in it and clouds passing through it, and the entanglement survived. 5 years later, the same link carried a teleportation experiment over 143 kilometers. Then one of Zeilinger's students, Jianwei Pan, went back to China, and with a great deal of institutional support, built something that no one had built before. In August of 2016, China launched a satellite called Mikius, named after an ancient Chinese philosopher, dedicated entirely to quantum experiments. It orbits at roughly 500 kilometers, and in 2017, it distributed entangled pairs of photons to 2 ground stations, separated by 1,203 kilometers, and the correlations held. Let me put that progression in a line, because the line is the argument. A tabletop, 600 meters, 144 kilometers, 1,200 kilometers, 4 orders of magnitude in 19 years, and the quantum weirdness did not degrade with distance the way everybody's intuition insists it should. Now, a photon is not a heavy object. Nobody should overclaim here. This is not a massive body in superposition, and we will get to why that distinction is the whole ballgame later on. But it already breaks the story you were told in your first year, because it means the domain of quantum mechanics is not small. It is whatever we can keep isolated. That is a completely different kind of boundary, and it is a boundary set by engineering rather than by nature. And here is the part that Fuentes cares about, and that almost nobody working on those experiments was set up to care about. At the altitude where satellites operate, general relativity is not a footnote. A clock on Mikius and a clock on the ground do not agree, because they sit at different depths in the Earth's gravitational well, and because one of them is moving at several kilometers per second. A photon climbing from the ground to the satellite arrives redshifted. Its frequency has dropped, because it climbed out of a gravitational potential. These are not exotic effects. They are the same effects that force the satellite navigation system in your pocket to correct itself by about 38 microseconds every day. So look at what has actually happened here. Quantum entanglement, the phenomenon that supposedly lives at the smallest scales, is now routinely maintained across distances where relativity has to be taken into account. The two regimes that were supposed to be separated by 30 orders of magnitude are meeting in the same experiment. And the way the community handled it, understandably, was to apply a correction and move on. You take the gravitational redshift, you take the Doppler shift from the relative motion, you fold both into the frequency, and you carry on with your cryptography. Fuentes did something else. She wrote a series of papers describing those photons using quantum field theory in curved spacetime, treating the Earth's geometry properly with the Schwarzschild solution, and asking what the curvature does to the quantum state of a wave packet climbing through it. And the answer is that it does more than shift the frequency. It changes the shape of the packet. A pulse of light is not a single frequency. It is a bundle of frequencies with a particular profile, and different parts of that bundle are affected differently on the way up. So the photon that arrives is not the photon that left with a number changed. It is a photon that has been distorted in a specific way by the geometry it crossed. That distortion degrades quantum protocols. It puts a ceiling on how well teleportation or cryptography can work over a satellite link, and it can be inverted. If you know how a known quantum state should be deformed by a given spacetime, then measuring the deformation is a measurement of the spacetime. The entanglement stops being the experiment. It becomes the instrument. This is not purely theoretical housekeeping, and there is a small piece of evidence that it is already biting. A group working in Germany on satellite quantum links had results they could not account for using the standard redshift correction. The whole group traveled to visit hers, because they wanted to know whether the curved spacetime treatment had something to say about what they were seeing. That is what a field looks like about 90 seconds before the loop closes for the first time. An experimental result nobody can explain, and a theorist with a framework that might explain it. But it is worth being honest about the state of play. Almost nobody is doing this. There is her work, and there is not very much else. The experiments themselves take the gravitational redshift into account and stop there, because for the purposes of getting a secure key from a satellite to a ground station, that is enough, and the people running them are not trying to test quantum field theory in curved spacetime. They are trying to build a network. I want you to ride one of these photons for a moment, because the abstraction hides something worth feeling. You are on a mountaintop on La Palma, in the dark, at about 2,400 meters, where the air is thin and cold, and the observatories are built precisely because there is so little atmosphere left above you. A crystal has just produced two photons that are entangled, which means that neither of them has a definite polarization, but that whatever one of them turns out to be, the other will match. One stays, one goes. You are on the one that goes. You cross 144 kilometers of open air over the Atlantic, at night, above the ocean, and the beam spreads and thins, and most of your companions are lost to turbulence and scattering, and a few arrive at a telescope on Tenerife, and the correlation is still there. The connection did not care about the distance, or the weather, or the sea. Now do it again, upward. You leave the ground station, and you climb. 500 kilometers of air thinning to nothing, and as you rise, something happens that has nothing to do with distance. The gravitational potential you are climbing out of takes energy from you, and your frequency drops. The clocks at the top of your climb are running faster than the clocks at the bottom. Not metaphorically, measurably. You arrive at the satellite carrying a quantum correlation that survived 1,200 kilometers, and carrying, folded into your own shape, the signature of a curved spacetime that no version of quantum mechanics knows how to talk about properly. Both theories, in one photon, at the same time. And there is one more thing to say before we move on, and it is the flag on all of this. Quantum field theory, in curved spacetime, the framework she is using, has never been directly confirmed by experiment. Not once. Flat space quantum field theory is the most precisely tested structure in science. It is what the accelerators at CERN and Fermilab are checking every day. But the version with gravity in it, the version that predicts Hawking radiation and the warm vacuum of an accelerating observer, remains untested, because its predictions live in places we cannot reach. Satellite quantum links are the first regime in which testing it becomes even imaginable, which means the machinery orbiting overhead right now, built for secure communication, is also the closest thing anyone has to a laboratory for a theory that has been on the books since the 1970s and has never once been checked. That is instrument number one. Instrument number two is smaller and much stranger, and it is already sitting on a bench. Let us step back for a moment and put the pieces we have on the table, because we are about halfway through, and the next thing I show you only lands if the previous things are still in your hands. We have a problem that has not moved in 110 years, and we have located the crack precisely. Quantum theory needs one absolute clock, and general relativity says there is no such thing. We have a diagnosis of why the problem has not moved, which is that a field with no measurements cannot correct itself, so it builds increasingly ornate machinery to defend a shape nobody has checked. The same failure that kept circles in the sky for 1,400 years. We have a physicist who arrived at this problem sideways, out of quantum optics, carrying a habit the theorists do not have, the reflex to ask what apparatus would settle it. And we have the first piece of that apparatus, which is that quantum entanglement now spans 1,000 kilometers, at altitudes where relativity is unavoidable, which means the two regimes have already met and nobody quite noticed. Now the second piece. And this one is smaller and closer and considerably harder to look away from. An atomic clock works on a simple principle. Atoms have internal energy levels, and the gap between two of those levels is astonishingly sharp. The same for every atom of that element, everywhere, forever, with no manufacturing tolerance and no drift. If you can find the exact frequency of light that bridges that gap, you have a frequency standard that nature itself maintains. So you trap a cloud of atoms, strontium, ytterbium, and aluminium ion. You cool them with lasers until they are barely moving. You hold them in an electromagnetic potential, and you shine light at them and tune it until they respond. The oscillation of that light is your tick. The clouds involved are small. A trapped sample of strontium in an optical lattice is a few millimeters across. Hold a grain of rice. You are holding something bigger than the entire timekeeping element of the most precise instrument humanity has built. And here is where it gets interesting, because these things have got so good that they have walked into general relativity from below. In 2010, a group at the American National Standards Laboratory, led by David Wineland, who would win a Nobel Prize 2 years later for the ion trapping methods that made it possible, did an experiment that ought to be more famous than it is. They took 2 aluminium ion clocks, and they raised one of them by 33 centimeters, not 33 kilometers, 33 centimeters, about the height of a stack of books, and they measured the difference in how fast the 2 clocks ran. Because there is one. Time runs slower deeper in a gravitational field, and a clock 33 centimeters closer to the floor is deeper in the Earth's field than one on the shelf above it. Einstein predicted that, in 1907, in 2010, somebody measured it across the height of a table lamp. The same experiment also measured the slowing of a clock, moving at about 10 meters per second, roughly the speed of a fast sprinter. Then it kept going. In 2019, an aluminium ion clock reached a systematic uncertainty of about 9 parts in 10 to the 19. And in 2022, within a month of each other, 2 papers landed that I think mark a genuine boundary in physics. A group at Gila, in Colorado, resolved the gravitational shift across 1 millimeter of a single strontium sample. 1 millimeter. Not between 2 clocks in 2 places, inside one cloud of atoms. The atoms at the bottom of the sample and the atoms at the top of the sample were measurably aging at different rates, and the fractional precision involved was around 7 parts in 10 to the 21. A group in Wisconsin published comparable work at sub-centimeter separations using a multiplexed clock in the same window. I want to translate those numbers because they are so far outside ordinary experience that they slide off the mind. A clock with a fractional uncertainty of 1 part in 10 to the 18 would gain or lose 1 second in about 32 billion years, more than twice the age of the universe. At the precision of the millimeter experiment, the equivalent drift is 1 second in more than 4 trillion years. These are the most precise measurements human beings have ever made of anything, and they are being made on a sample the size of a grain of rice, in a room, by people who will go home for dinner. It is worth pausing on how ordinary the applications of this are, because it makes the precision feel real rather than decorative. Clocks of this class are what synchronize the world. Financial exchanges timestamp trades against them. Power grids use them to keep alternating current in phase across a continent. Radio telescopes on different continents combine their signals into a single virtual instrument by agreeing on time to within a fraction of a nanosecond. And the satellite navigation in your car depends on a chain of atomic clocks so completely that if you switched off the relativistic corrections it applies, your position would drift by about 10 kilometers in a single day. Relativity is not a philosophical topic in that system. It is load-bearing infrastructure, and it is bearing load in your pocket. There is a small human moment attached to this that I find hard to shake. A few years before those papers, Fuentes was talking to a colleague named Patrick Gill at the United Kingdom's National Physical Laboratory, which is the institution that maintains British measurement standards, the people whose job is time and length and mass. She told him that they were about to have a problem. "Your clocks are getting so precise," she said, "that the proper time at the bottom of your atomic sample is going to differ measurably from the proper time at the top." And the response, entirely reasonably, was, "Yes, but we are not too worried about that right now." About 6 months later, the two papers came out. Nobody did anything wrong in that exchange. She was thinking about where the physics was heading. He was thinking about what his instrument needed this year. That is the correct division of labor, and both of them were doing their job. It is just that the future arrived on the shorter timescale. So take stock of where the two theories now stand physically, because this is the thing I want you to hold. Quantum mechanics has been demonstrated across 1,200 kilometers. General relativity has been demonstrated across 1 millimeter. The territories have not merely overlapped, they have crossed straight through each other. There is now a class of object, sitting on laboratory benches in half a dozen countries, that is simultaneously a quantum system requiring quantum mechanics for its description, and a system in which the curvature of spacetime is a resolvable, measured, everyday effect. For the entire history of the unification problem, the standard reason for not attempting an experiment was that the regime where the theories meet is unreachable. You would need energies of a kind no accelerator will ever produce, or lengths so small that no instrument could resolve them. And that argument was correct about one route to the problem. It has quietly stopped being correct about all of them. Fuentes tells a story about this that goes back to when she first started saying she wanted to measure relativistic effects with quantum systems. Her colleagues in general relativity laughed at her, not cruelly. They simply pointed out the obvious thing, which is that at small scales, space-time is flat, utterly flat. Take a region a millimeter across, and there is no curvature there worth the name. You will not see anything. They were right about the curvature. They were wrong about the instrument, because the question is never whether an effect is small. It is whether the effect is larger than what you can measure, and a device that keeps time to 1 part in 10 to the 21 has changed the answer to that question for an entire class of experiments. That distinction is worth carrying with you generally, because it is one of the most reliable ways that confident predictions of impossibility go wrong. An effect being tiny is a statement about nature, and it does not change. Your ability to resolve it is a statement about engineering, and it changes constantly, sometimes by orders of magnitude within a single career. Every time someone says a thing can never be measured, what they are usually saying, without noticing, is that it cannot be measured with the instruments they happen to be able to imagine. So now both theories apply to the same grain of rice, at the same time, in the same laboratory. Which means somebody, quite soon, is going to have to say what happens when they disagree. And it turns out, somebody already has to, right now, this year, and the answer they have arrived at is one of the most quietly astonishing things I have come across in physics. Here is the situation the world's timekeepers are currently in. Their clocks are limited by statistics. When you measure the frequency of an atomic transition, you are asking a lot of atoms the same question and taking an average. And the uncertainty in that average shrinks the way averages always shrink, as 1 over the square root of the number of atoms. Ask 1,000,000 atoms, and you do 1,000 times better than asking 1. That is the ordinary rule, and every clock ever built has obeyed it. But there is a way around it, and it comes from quantum information theory. If you entangle the atoms instead of letting them answer independently, the uncertainty shrinks as 1 over the number of atoms rather than 1 over its square root. This is called the Heisenberg limit, and it is the genuine floor set by quantum mechanics. For 1,000,000 atoms, it buys you a factor of 1,000 in precision. So of course that is what everyone wants to do next. You have the best instrument in the world, and there is a known route to making it 1,000 times better. Nobody is going to decline that. Now put the two facts together. Fact 1. To get past the statistical limit, you have to entangle the atoms. Turn a crowd of independent systems into one quantum object spread across the trap. Fact 2. That trap is now, demonstrably, tall enough for time to run at different rates inside it. The millimeter experiment proved that. The atoms near the bottom of the sample sit deeper in the Earth's gravitational field. Their proper time runs slower than the proper time of the atoms at the top. Measurably, reproducibly, in print. And now write down the equation that describes what your entangled atoms do next. You cannot. I want to be precise about why, because this is the exact point where 110 years of abstraction turns into a practical obstruction on a bench. The Schrödinger equation, which is the machinery for evolving a quantum state forward, has a derivative with respect to time on one side. One derivative, one time. It requires you to name the single parameter along which the whole state is developing. So which time do you use? Not a rhetorical question. Your quantum object occupies a region in which time demonstrably runs at more than one rate. There is no fact of the matter about which of those rates belongs to the state, because the state is not located anywhere in particular. That is what entanglement means. Every option is wrong. Use the time at the bottom, and you are wrong about the top. Use the top, and you are wrong about the bottom. And you cannot do what physicists do for GPS satellites, which is calculate the shift and correct for it, because the correction procedure assumes you have separate systems, each carrying their own clock. Once they are entangled, you do not have separate systems. You have one thing, in a place where time is not one thing. That is the collision, not in a black hole, not at the birth of the universe, not at an energy scale 1,000,000 billion times beyond anything we can build. In a vacuum chamber, in a metrology laboratory, this year, in a device that people are actively trying to sell. And notice how different this is from the way the problem is normally presented. The standard story about quantum gravity is that the two theories only fight each other in places nobody can go. The interior of a black hole, the first fraction of a second of the universe, the scale at which spacetime itself supposedly comes apart. That framing is comfortable, in a way, because it puts the contradiction safely out of reach and turns it into an object of contemplation rather than a chore. What is happening in these clocks is not that. It is the same contradiction in an ordinary room with a purchase order attached to it. The two theories are not disagreeing about the unimaginable. They are disagreeing about a cloud of strontium the size of a grain of rice, and somebody has to write down a number this quarter. So what do the experimentalists actually do? They use the proper time at the center of the trap. Take the middle of the sample, take the rate of time there, put that number into the equation, and carry on. And it works well enough. That is the part that unsettles me. It is not that the patch fails and everyone panics. It is that the patch is fine. You get a number out, the clock ticks, the paper gets published. For the purpose of comparing two clocks to 20 decimal places, using the center of the trap is probably good enough. And the people doing it are not fools and are not hiding anything. They know it is an approximation. If you ask them, they will tell you. Fuentes' assessment of it is blunt, and I think exactly right. From a theoretical point of view, she says, this is not the right thing to do. It is a patch. And the cost of the patch is not that you get a wrong answer. The cost is that you lose the chance to find out what the right answer would have been. Because look at what is being thrown away here. For 110 years, the reason nobody could make progress on unification was that there was no measurement to constrain it. Not a bad measurement, none. And now there is an experiment. A real, running, funded, published experiment that has walked directly into the gap between the two theories and is producing data from inside it. That data is the first physical information anyone has ever had about what happens when quantum mechanics and general relativity are forced to describe the same object at the same time. And the way it is being processed involves an approximation whose function, whether anyone intends it or not, is to make the problem go away before it can be looked at. I said at the beginning that we would come back to a room in Padua from a completely different direction, and here it is. Nobody in this story is Cremonini in the cartoon sense. Nobody is being obstinate. Nobody is defending an ideology. What is happening is that a group of careful, competent, well-motivated people have an instrument that has arrived at the edge of the deepest question in physics, and they have a deadline and a funding body and a specification to meet, and there is a reasonable-looking approximation available that lets them meet it. So they take it. Of course they take it. In their position, I would take it. And the telescope goes unlooked through anyway, not refused, just never quite picked up, because everybody had something more pressing to do that week, and the week after that. That is the thing I want you to sit with tonight, because it is much more disturbing than the version where somebody refuses out of arrogance. Arrogance you can spot. Arrogance you can argue with. What is actually happening is that the refusal is distributed, spread across a dozen individually sensible decisions made by people who are each optimizing something local and legitimate, none of whom is responsible for the fact that in aggregate the question does not get asked. Nobody chose it. It is nobody's fault. It is simply what happens. Fuentes went and visited the group at the National Physical Laboratory to make more or less this argument to them in person. Her pitch was not that they should abandon their approximation. It was more interesting than that. She said, "You have a theory. Your theory is that taking the proper time at the center of the sample is good enough. That is a theory. It is not a very good one, but it is specific, and it makes predictions, and you have a machine that can test it. So let us use your experiment. Let us take the theory we have, run it against the instrument, look at where it fails, and use the failure to build a better one. That is the loop. That is exactly the loop from the atom and the microscope, offered in the one place where the loop has never once closed. Whether anyone takes her up on it is a different matter, and I do not know the answer. But there is a second half to her argument, and it is not a complaint at all. It is a construction, because if the problem is that we no longer know what a clock even is when the thing doing the ticking is quantum and the place it is ticking in is curved, then perhaps the honest response is to stop patching the old definition and go back and build a new one from the ground up, which is precisely what she spent 15 years doing, and it produced something nobody expected. Einstein had a favorite toy, and if you have ever seen a derivation of time dilation, you have met it. Take two mirrors facing each other and bounce a single pulse of light between them. Every round trip is a tick. That is your clock, the simplest possible clock, built out of nothing but the constancy of the speed of light. And now set the whole apparatus moving sideways. From the point of view of somebody watching it go past, the light no longer travels straight up and down, it travels diagonally, because the mirrors have moved on while it was in flight. A diagonal path is longer than a vertical one. The light cannot go faster to compensate, because nothing can. So each tick takes longer. The moving clock runs slow. It is one of the most elegant arguments in physics, and it is usually where the story ends. It is a teaching device. Nobody builds one. Fuentes' group asked what happens if you take it seriously as a physical object and quantize it. So, keep the two mirrors, but replace the bouncing pulse with a quantum electromagnetic field filling the cavity between them. Once you do that, the picture changes completely. You can no longer talk about a photon at a position going back and forth. What you have instead is a field that decomposes into an infinite set of modes, standing wave patterns, each with a sharp, definite frequency, each filling the entire cavity. The photons in those modes have no location at all. They are smeared through the whole box, which is exactly what quantum field theory says they should be, and the clock's tick is no longer a bounce. It is the oscillation of one chosen mode. Now move the box. This is where it becomes genuinely hard, and the difficulty is worth respecting, because it explains the timescale. At first, the only version anybody could solve was in flat space, with the mirrors oscillating back and forth sinusoidally. That case has a name, the dynamical Casimir effect, and it is remarkable in its own right. So let me detour for a second, because it is one of my favorite results in physics. If you accelerate a mirror through empty space, photons come out. Not photons that were hiding there. The vacuum in quantum field theory is not nothing. It is the lowest energy state of a field, and it has structure, and a boundary moving through it can convert that structure into real detectable particles. Gerald Moore predicted this in 1970. It sat unobserved for 41 years, because you have to shake a mirror at a substantial fraction of the speed of light, which is not something you can do with a mirror. In 2011, a group finally managed it by using a superconducting circuit whose electrical properties could be varied so fast that it behaved as though it were an oscillating boundary and light came out of the vacuum. That is the closest laboratory cousin anyone has to Hawking radiation, and it works. But flat space and a shaking wall was not what Fuentes wanted. She wanted the real thing, a quantum clock moving through genuinely curved spacetime, so she could ask what happens when quantum states and gravitational time dilation are forced to interact. That took more than 15 years. I want to say that plainly, because scientific stories are usually told with the weighting removed. 15 years of not being able to solve the equations. Not 15 years of thinking about it occasionally. 15 years in which the obstruction was a specific piece of mathematics that would not yield, and every attempt to get around it produced something that only worked in a special case. This is the ordinary texture of theoretical physics, and it almost never makes it into the story. The papers arrive looking inevitable. What is missing from them is the decade in the middle where nothing worked, and where the honest description of the project would have been that a small group of people were quietly failing in public. The breakthrough came from working with a colleague at Nottingham named Jorma Luco, a specialist in quantum field theory in curved spacetime, and together they developed a methodology general enough to handle the problem. By 2023, they had a clock model that could be placed in the actual geometry around the Earth, described with the Schwarzschild solution, and asked how it ticks. Two things came out of that, and both are strange. The first is a genuine surprise, the kind of result nobody would ever have guessed without doing the calculation. When you move the quantum clock, the dynamical Casimir effect creates photons inside it. Those photons carry energy. That energy is part of the clock, and it changes the clock's own time dilation. Think about what that means. The clock's motion generates particles from the vacuum, and those particles alter the rate at which the clock runs. The instrument modifies the quantity it exists to measure through a purely quantum mechanism, with nothing external interfering at all. This is not measurement disturbance in the usual sense, where a probe nudges the thing it probes. This is a clock that changes its own time by being moved. The second thing is deeper, and I think it may end up being the most important idea in this whole video. Because the tick is carried by a quantum field, the clock inherits quantum uncertainty, and that means there are limits, set by physics, not by workmanship, on how precisely such a device can measure the geometry it sits in. Measure a duration extremely well, and your localization degrades. There are trade-offs baked into the structure, arising from the fact that the states you use are quantum states, with minimum uncertainty relations between the quantities describing them. Sit with the shape of that. The instrument you are using to measure spacetime is made of the thing it is measuring. It is not standing outside, looking in. There is no outside. And when you work out carefully what such an instrument can and cannot resolve, you find that spacetime may be knowable only to a limited degree from within it. Not because our engineering is poor, but because any ruler is built from the material it measures. I want to be careful not to overclaim, because there is a version of this idea that gets thrown around loosely, usually attached to the Planck scale and delivered with more confidence than anyone has earned. This is not that. This is a specific, worked-out set of constraints for a specific class of quantum clock, and it is a long way from a general theorem about the knowability of spacetime. But it is the first time I have seen that question approached from the direction of an actual instrument rather than from a philosophical argument, and instruments have a habit of being more honest than arguments. And then there is the third result, which is the one that points forward. In the quantized light clock, every spatial slice of the cavity has its own proper time. There is no single rate. So how do you define what the clock reads? Their answer was to stop looking for a local rate and instead define the clock's time from the collective oscillation of the entire field, a property of the whole object, rather than of any point in it. Now go back to the problem from the last part. An entangled atomic clock is a single quantum object spread across a region where time runs at different rates, and the working patch is to pick the middle. But if clock time can be rebuilt as a collective property for a light clock, perhaps it can be rebuilt the same way for atoms, not a patch. A replacement definition, derived rather than assumed, that does not require you to pretend the sample has one clock. That is what a doctoral student in her group is working on now. There is nothing published. There may be nothing for years. She says plainly that they do not have much to say about the atomic case yet. But you can see the shape of it, and the shape is the loop closing. A theory that fails, an experiment that has walked into the failure, and somebody rebuilding the definition rather than patching the symptom. That is the clock. Now for the mass, and the mass is where it gets difficult. If you asked Ivette Fuentes to name the single most interesting unanswered question in physics, she would not say what dark matter is, or what happened before the Big Bang, or whether the universe is fine-tuned. She would say this: what happens when a mass is in a superposition of two locations? That sounds modest. It is not. Let me build it up carefully, because everything in the last part of this video depends on understanding why that particular question is the sharpest knife available. We know that quantum objects can be in superpositions of position. That has been demonstrated for decades. We also know that electromagnetic fields inherit the quantum state of their sources. Put an electron in a superposition of two places, and the electric field it produces is in a superposition of two configurations. That is not speculative. Quantum optics is one of the best tested areas of physics, and this is bread and butter within it. So run the same argument with gravity. Put a mass in a superposition of two locations. Mass produces a gravitational field. Gravitational field means curvature of spacetime. Therefore, the geometry itself, the shape of space, the rate at which time flows, would be in a superposition of two configurations. Is that what happens? Nobody knows. And here is the thing that makes it maddening. Not one of our theories can answer it. Quantum mechanics cannot, because it has no gravity in it. General relativity cannot, because it has no superpositions in it. And quantum field theory in curved spacetime, that enormous, sophisticated piece of the puzzle we have been leaning on all through this video, cannot either, and the reason is important. That framework assumes a fixed background. You choose a spacetime that solves Einstein's equations, you freeze it, and then you let quantum fields live on top of it. What the fields are forbidden to do is bend the thing they live on. It is a one-way street. So the moment you ask what a superposed mass does to geometry, you are asking the one question the framework was constructed to avoid. That is why she calls it the most interesting question. It is the smallest question that no existing theory can touch. Now, if the mass is tiny, a single atom, say, then presumably you do get a gravitational field in a superposition, in some faint and technically legitimate sense. Roger Penrose would say that already counts as quantum gravity. You have geometry in a quantum state. But that is not where the interest lies. The interest is in whether that situation is stable, and Penrose's answer, worked out over decades, is that it is not. His argument runs roughly as follows, and I will keep it at the level where you can feel the force of it. Take your mass in two places. Each branch of the superposition has its own gravitational field, and therefore its own spacetime, and therefore its own notion of what it means to stand still and let time pass. Now try to describe the whole thing in a single quantum state. Describe it from a Newtonian point of view, and you write down one wave function. Describe it from an Einsteinian point of view, using free-fall coordinates, as general relativity insists you may, and you write down a different one. In quantum theory, two descriptions are allowed to differ by an overall phase and still count as the same physical state. Penrose shows that these differ by more than a phase. The two descriptions are not the same state, and there is no way to make them the same. So something has to give, and Penrose says what gives is the superposition. He quantifies the discrepancy as an energy, specifically the gravitational self-energy of the difference between the two mass distributions. Then he treats that as an energy uncertainty and pushes it through the relationship between energy uncertainty and lifetime. The same relationship that tells you why unstable particles decay when they do. Out comes a timescale. Below a certain mass, the superposition survives essentially forever. Above it, it collapses almost instantly. If Penrose is right, this is not a small result. It means gravity is the reason the world looks solid. It means the answer to why you never see a coffee cup in two places is not that the coffee cup is complicated or that the environment is watching, but that space-time itself will not tolerate the ambiguity. And it means the measurement problem in quantum mechanics and the unification problem in physics are not two problems. They are one problem, and solving either solves both. I want you to be inside this rather than outside it, so let me take you there. Imagine you are the mass, not a person, a small crystal, a bead of glass, something with real weight, held in a trap in a cold and silent chamber. A pulse of light arrives and splits you, and now there are two of you, a fraction of a hair's width apart, and neither one is more real than the other. Here is what makes this different from every other superposition you have ever heard about. You are heavy, so each of you is bending the space around you, very slightly, into a well. And the well made by the left one is not in the same place as the well made by the right one, which means that the geometry, the actual shape of the room, the actual rate at which time passes for a point sitting just beside you, is now undecided in a way that has never been undecided before. It is not that we do not know which well is there, it is that the question of what shape space-time has, right there, right now, has no answer. And then, if Penrose is correct, the ambiguity does not last. There is a clock running on it, and the clock is set by your own weight, and when it runs out you are in one place. Not because anything looked at you, because the universe cannot hold two shapes of itself in the same location for longer than that. And the heavier you are, the shorter the weight. That is the prediction. It is falsifiable, which puts it in a rare and honorable category among ideas about quantum gravity. So how close are the experiments? Here is the ladder, honestly. Electrons in superpositions of two paths, routine, and has been since the middle of the last century. Then molecules. Marcus Arndt's group in Vienna interfered molecules of 60 carbon atoms in 1999. Footballs of carbon, genuinely large objects, going through two slits at once. And by 2019, they had pushed it to molecules of around 2,000 atoms, 25,000 times the mass of a hydrogen atom. Those superpositions last milliseconds. Gravity does nothing to them. They sit there, in two places, entirely stable. Which is exactly what Penrose predicts, by the way. 2,000 atoms is nowhere near heavy enough. The prediction is not that all superpositions collapse. It is that they collapse above a threshold, and below it they are fine. Next rung, Marcus Aspelmeyer's group, also in Vienna, took a silica nanosphere, a bead about 100 million times the mass of a hydrogen atom, visibly enormous by quantum standards, levitated it in a laser trap, and cooled its motion into the quantum ground state. That was 2020, so we now have a genuinely heavy object behaving quantum mechanically. But being in the ground state is not the same as being in two places. Nobody has managed to split one. And in 2024, at Southampton, Hendrik Ulbricht's group and collaborators in the Netherlands and Italy measured the gravitational pull on a levitated magnetic particle weighing about 0.5 milligram, held above a superconductor at 1/100th of a degree above absolute zero. The force they measured was 30 attonewtons, 3 times 10 to the minus 17 newtons. To put that in the body rather than the notation, that is roughly 10,000 times smaller than the weight of a single red blood cell. That measurement is entirely classical. There is nothing quantum about it. Its significance is the flaw. It shows that force sensing has descended into the range where the gravitational pull of a small object is measurable at all, which is the precondition for ever asking a quantum question about it. So we have quantum behavior up to 100 million atomic masses, superposition up to 2,000 atoms, and gravity sensing down to 30 attonewtons. And all three of those numbers were unimaginable 30 years ago. Now the requirement. To test the Penrose prediction, the calculation Fuentes did with him says you need something like 1 billion atoms in superposition, possibly 10 billion, against a record of 2,000. That is the gap, 6 orders of magnitude, minimum. And the reason it is not hopeless is that there exists one system in the universe where 1 billion atoms already behave as one quantum object. When Penrose first started telling Fuentes about his proposal and about the experiments people were attempting, she noticed something that nobody else seemed to be treating as a problem. Every one of those experiments was using a solid, mirrors, beads, little rods, membranes, diamonds, nanoparticles of silica, all of them lumps of material, and all of them running into the same wall, which is that you cannot get a solid cold enough. There is always residual motion. There is always thermal noise. Cooling a lump of matter to the point where its quantum behavior is not drowned out by its own jiggling is extraordinarily hard. And that difficulty, not the physics, not the theory, the refrigeration, is why progress on massive superpositions has been so slow. She came from a different tradition, and in that tradition there is an object that solves precisely this problem, and she says without hesitation that it is her favorite system in physics. Let me tell you what a Bose-Einstein condensate is, because it is one of the genuinely lovely things human beings have made. Start with something you learn in a first course on quantum mechanics. Take a single particle and put it in a trap, a potential well of some kind. Ordinarily, it moves around inside. But cool it all the way down to the lowest energy state available, and something odd happens. It does not sit still at the bottom. It becomes delocalized across the entire well. There is no fact about where it is. It occupies the whole trap as a single smeared quantum state. And that is not ignorance on your part. There is nothing more to know. Now the trick. Atoms of the right kind are bosons, and bosons are permitted to occupy the same quantum state as each other in unlimited numbers. Fermions, electrons for instance, are not. They refuse, and that refusal is why matter takes up space and why chemistry exists. But bosons are gregarious. So if you take a cloud of bosonic atoms and cool it far enough, they do not settle into a stack of different states. They all fall into the same one. Every atom in the cloud enters the ground state of the trap together, delocalized across the whole thing, indistinguishable, moving as one. That is a condensate, and it is the largest object we know how to make that behaves as a single quantum system. How cold is far enough? In 2003, a group working with sodium reached 450 picokelvin. Let me put that on a ladder so you can feel it. Liquid helium boils at about 4.2 degrees above absolute zero. The space between the stars, warmed by the afterglow of the Big Bang, sits at 2.7 degrees. The levitated magnet in the Southampton gravity experiment was held at about 1/100th of a degree, and a condensate is 450 trillionths of a degree, under half a billionth of a degree above absolute zero, roughly 6 billion times colder than deep space. There is nowhere in the natural universe that cold. Not the darkest void between galaxies, not the interior of the coldest nebula. As far as anyone can tell, the coldest places that have ever existed since the universe began are inside a few dozen laboratory vacuum chambers on this planet. I would like you to stand next to one for a moment. The chamber is small and unremarkable. Steel, ports, windows, cables, the untidy geometry of real equipment. Inside, held in a cage of laser light and magnetic fields, is a cloud of atoms, perhaps 1/10 of a millimeter across, and it is faintly visible if you know how to look. And as the last stages of cooling take hold, that cloud stops being a crowd. The atoms cease to be a collection of things at different places doing different things. 1 billion of them settle into one state, and there is no longer a fact about which atom is where, because the question has stopped applying. Not 1 billion little objects. One object, with 1 billion atoms worth of weight, and no positions inside it. And it is colder than anywhere in the universe, in a room, 3 meters from a person drinking coffee. Now, the reason this matters for our problem is the number. The Penrose test needs roughly 1 billion atoms in superposition. Condensates already reach that size. The largest by atom count are made of hydrogen, and one made at the end of the 1990s held about 1 billion atoms. So we have the mass. We have the coldness by 10 orders of magnitude over anything a solid can manage. We have the system. Fuentes and Penrose worked out the details together, and the paper they published with Richard Howell in 2019 asks exactly this. How would you test the collapse prediction with a condensate? They looked at whether the shape of the cloud helps. Condensates can be squashed into pancakes or drawn out into cigars, and the distribution of the mass affects the gravitational self-energy, which is the quantity that sets the collapse time. They looked at losses, because atoms leak out of these traps constantly, and they arrived at the threshold, about 1 billion atoms, maybe 10 billion, before the effect Penrose predicts becomes visible. And now the wall. Having 1 billion atoms in one quantum state is not the same as having 1 billion atoms in 2 places. To run the test, you need the entire condensate on the left and the entire condensate on the right, simultaneously, all of them, together, in both locations. States like that have a name. Physicists call them noon states, for the way you write them down. N particles here and 0 there, plus 0 here and n there. The record for making one of those with atoms is 2. Not 2,000, not 200, 2 atoms. One of Fuentes' own collaborators, Christopher Westbrook, holds it. With photons rather than atoms, people have managed around 5. So the situation is this. We can make 1 billion atoms behave as one quantum object, colder than anywhere in the universe. We can put 2,000 atoms in 2 places at once. And to answer the deepest question in physics, we need to put 1 billion atoms in 2 places at once, and the current record for that specific thing is 2. I find that number genuinely difficult to sit with, and I want to be clear about why. It is not disappointment. Everything on the other side of the ledger is extraordinary. The coldness, the size, the control, all of it achieved within a single working lifetime. The difficulty is the collision between the grandeur of what has been built and the smallness of what remains. One gap, 6 orders of magnitude wide, in one specific technical capability. And on the far side of that gap is the first experimental information human beings would ever have about whether spacetime is quantum. There is also a piece of honest bookkeeping to add here, because the collapse program is not merely a proposal awaiting a verdict. Parts of it have already been tested and have already failed. There is a version of the Penrose collapse idea developed with the physicist Lajos Diossi that in its simplest parameter-free form predicts that collapsing matter should emit a faint spontaneous radiation. In 2021, an experiment buried under a mountain in Italy went looking for that radiation in one of the quietest places on Earth and did not find it. The simplest version is dead. The broader framework survives in modified form, and Penrose accepts the result. That is what a live scientific idea looks like. It is already being shot at, and some of it is already down. It is also worth knowing that the condensate is not the only route being attempted, because a fair account should include the competition. In 2017, 2 groups independently proposed something ingenious. Take 2 masses, put each of them in a superposition, place them near enough that their mutual gravity matters, and see whether they become entangled with each other. The reasoning behind it is elegant. There is a theorem in quantum information theory saying that 2 systems cannot become entangled through a purely classical channel. So if gravity entangles them, gravity is not classical. It is a different apparatus and a different route, aimed at the same target, and its existence strengthens rather than weakens the argument of this video. Because it means the idea that quantum gravity is testable on a bench is not one person's eccentricity. It is a small but growing program. Which brings us to the last piece, and the one that made me want to make this video. Because everything I have described so far is somebody trying to reach a threshold. Fuentes did something else. She looked at the entire strategy the field was using to get there and decided it was pointed the wrong way. To see what she did, you first have to see the assumption that everybody else is standing on, and the assumption is so deeply embedded that it does not look like an assumption at all. It looks like arithmetic. Here is how you measure gravity with atoms. You take an atom and you hit it with a laser pulse, which splits it into a superposition of 2 states with slightly different momenta. Those 2 versions of the atom now drift apart along different trajectories, both in freefall. You let them fly. Then you hit them with more pulses to bring them back together, and they recombine and interfere. And because the 2 paths pass through slightly different parts of the gravitational field, the interference pattern carries a phase that tells you what that field was. This is an atom interferometer, and it is one of the triumphs of modern physics. It works. It is commercial. Philippe Bouillet, a French physicist, co-founded a company to build and sell these things as gravimeters for surveying and geophysics and civil engineering. Other groups have done the same. If you want to know whether there is a cavity under a road, you can buy an instrument that measures it by asking an atom to fall in 2 ways at once. Now the arithmetic. The sensitivity of that device depends on how long the 2 halves of the atom spend apart, and it does not depend on it gently. It goes as the square of the time of flight. Double the flight time, and you quadruple the sensitivity. And flight time, for something in free fall, means height, means length, means size. So the entire field has one lever, and everybody is pulling it. A commercial gravimeter is about 1 meter tall, and you cannot make it smaller without losing precision. That limit is why they look the way they look. Mark Kasovich's group at Stanford built a 10-meter tower. There is an instrument at Fermilab called MAGIS, 100 meters of strontium interferometer. In Germany, there is a drop tower 146 meters tall, and researchers put an atom interferometer at the top and let it fall to buy themselves 9 seconds of free fall. Bouillet took an interferometer up in an aircraft and flew parabolas so the whole apparatus was falling, and he built one underground in the south of France, in a low-noise laboratory inside a mountain, with arms 300 meters long. Then look at the light-based detectors. The gravitational wave observatory that made the first detection has arms 4 kilometers long, each one an evacuated tube running to the horizon. Its European counterpart has 3-kilometer arms, and because even that is not enough for the frequencies people want to reach, the plan for the next generation is to go to space and fly 3 spacecraft in a triangle with sides of 2.5 million kilometers. A meter, 10 meters, 100 meters, 146 meters, 300 meters, 4 kilometers, 2.5 million kilometers. That is a field with one idea about how to become more sensitive, executed with enormous skill and enormous budgets over 4 decades. And I want to be careful here, because it would be cheap to mock it, and it does not deserve mockery. Big worked. The first direct detection of a gravitational wave in 2015 is one of the great achievements in the history of measurement, and nothing on a tabletop would have caught it. The scale was necessary, but scale being necessary for one job is not the same as scale being the only lever there is. And I want you to notice the shape of what has just happened, because we have met it before tonight. Somewhere along the way, a true statement, for this design, precision scales with size, quietly became a general one, to measure gravity better, build something bigger. Nobody decided that. It was never voted on. It simply became the water the field swims in, to the point where an entire international roadmap consists of the same instrument at successively larger sizes, and the interesting question becomes how to fund the next length, rather than whether length is the right currency. That is a perfect figure, not a wrong theory. A wrong assumption about what the answer has to look like, so deeply held that the machinery built to satisfy it stops looking like machinery and starts looking like the shape of the problem. The circles were one. The demand that gravity be quantized, the way the other forces were quantized, may be another. And the assumption that a better detector is a longer detector is a third, sitting not in the theory at all, but in the engineering. Some people have pushed back against it within the existing design. There is lovely work by Guglielmo Tino's group in Italy on slowing the atoms with additional lasers so that you get long interrogation times out of a small apparatus, squeezing more sensitivity from less height. That is real progress. But it is still an argument about how much length you can do without. Fuentes describes herself cheerfully as a contrarian. She says her husband calls her a rebel. If everyone is going one way, she wants to go the other, and she admits this makes her difficult about ordinary things. She does not want to see the film everybody is seeing. In science, she says, it has paid off. So when she looked at that ladder of ever larger machines, the question she asked was not how to climb it faster. It was, why is precision tied to size in the first place? And the answer is specific. It is tied to size because these instruments interfere in space. The signal comes from 2 paths separated by a distance, so the distance is the resource, and buying more of it means building something longer. So do not interfere in space. Interfere in frequency. Here is the idea. Take a Bose-Einstein condensate. It is not just a cloud of cold atoms. It is a quantum object that can vibrate. And its vibrations, sound waves in the condensate, collective ripples running through it, behave as particles in their own right. Physicists call them phonons, and you can prepare those phonon modes in genuinely non-classical states, which you can only do because the condensate is at 1/2 billionth of a degree, and there is essentially no thermal noise to swamp them. Now let a space-time distortion pass through. A gravitational wave stretches and squeezes space as it goes by. That stretching changes the boundary conditions of the condensate, and the phonon modes respond. They mix, they shift relative phase, and one mode leaks into another. And the precision with which you can detect that is limited not by how far apart you can hold 2 paths, but by how long you can keep those quantum states coherent. The resource has changed. It is no longer length, it is time. And an instrument whose resource is coherence time does not need to be large. It needs to be quiet and cold and undisturbed. The condensate in Fuentes' proposal is somewhere between 50 and 100 micrometers across, about the width of a human hair, and the whole experiment fits on a table in an ordinary room. Let me walk you through the two rooms, because I think this is the moment where the whole video turns. Room 1 is 4 kilometers long. You are standing at the corner station of a gravitational wave observatory, and there is a steel tube leaving the building and running away from you until it disappears into the haze. Inside that tube is one of the largest sustained vacuums on Earth. Another identical tube runs perpendicular. Every part of this machine is enormous, because the physics said it had to be. The signal is a change in length of a fraction of the width of a proton, and to see a fractional change that small, you need a very great deal of length to take the fraction of. Hundreds of people, decades, hundreds of millions of dollars, and it worked. Room 2 is an ordinary laboratory. There is a bench. On the bench is a vacuum chamber the size of a microwave oven, with windows in it and lasers pointed through them and a mess of cables. Inside, in the middle, is a cloud of atoms about as wide as a hair, colder than anything in the universe. It is silent. Nothing is moving. And the proposal on the table says that this can hear a gravitational wave that the 4-kilometer machine cannot. Not because it is more sensitive in the same way, but because it is not listening in the same currency. It is not measuring a length. It is listening to a ringing, and its limit is how long it can hold still. Now, there is an important honesty in this, and Fuentes states it herself. The condensate detector does not compete with the big observatories. It works at high frequencies, well above the band where colliding black holes and neutron stars live. So it is not a rival. It is a window onto a part of the spectrum nobody currently has an ear in at all, where the candidate sources are exotic and speculative, and where, if there is nothing to hear, the answer may simply be silence. And the design lineage is worth knowing, because it closes an old loop. Back in the 1960s, at Maryland, a physicist named Joseph Weber built the first gravitational wave detectors, and they were not interferometers. They were solid aluminium cylinders weighing over a ton, and the principle was that a passing wave would set the bar ringing at its resonant frequency. He announced detections in 1969. Nobody could reproduce them, and the claims fell apart, and the resonant bar approach was largely abandoned in favor of the long-armed interferometers. But the principle was never wrong. What was wrong was the temperature. Weber's bars were, at best, at a few degrees above absolute zero, and the thermal jostling of a ton of aluminium at that temperature swamps everything. A condensate does the same job, vibrations ringing in response to spacetime, 10 orders of magnitude colder, with the vibrations prepared in states that have no classical description at all. It is Weber's idea, rebuilt as a quantum object, 60 years later. And once you have that instrument, it is not only a gravitational wave detector. Fuentes has applied the same frequency interferometric approach to searches for dark matter, to searches for signatures of dark energy, and to measuring local gravitational fields, which she has patented because a small precise gravimeter has obvious commercial value. That last point is worth a moment, because it is how instruments actually get built. Precision optics and vacuum technology did not arrive in physics because physicists funded them. They arrived because industry wanted them, and physics inherited the capability. If frequency interferometry produces a gravimeter somebody wants to buy, the fundamental physics experiment gets built on the back of the commercial one. Which leaves one question: does any of it work? So, is this the breakthrough in modern physics we have been waiting for? I have been holding that question for about 2 hours, and I am going to answer it plainly, in both directions, because it deserves both. Start with what is not true. Nothing here has been confirmed. The condensate gravitational wave detector is a proposal on paper. It has not been built. The frequency interferometry approach has not returned a measurement of anything fundamental. The Penrose collapse prediction has not been tested, and the technical requirement for testing it is 6 orders of magnitude away, with no clear route across. The high-frequency band that the tabletop detector would listen in might be empty. Fuentes' own unification work, the thing she is now building an experiment for, with Philippe Bouillet and Christopher Westbrook, on funding she has recently raised, is not published. She describes it herself as a step, not the full thing. And a generation of physicists has been promised imminent quantum gravity data before, and did not get it. If you want a headline, there is no headline. Nobody has solved anything. And now the other direction, which I think is more important, and which took me the whole of this video to see properly. We have spent 110 years assuming that the breakthrough we were waiting for would be an equation. That is what the word means in this context. Somebody will find the right mathematics, and it will click, and gravity and the quantum will fold into one another, and the person who does it will be the next Einstein. Every account of this problem is written as though that is the shape of the thing we are waiting for. But look at how physics has actually moved, every single time. The Greeks had the idea of the atom for 2,000 years, and it went nowhere, and then somebody built an instrument, and within a century we had quantum mechanics. People stared at the sky for tens of thousands of years and produced beautiful, careful, entirely wrong cosmologies. And then somebody ground a piece of glass, and within 3 centuries we had the expanding universe. Michelson and Morley built an interferometer to measure the ether and found nothing at all, and that nothing became special relativity. The instrument does not follow the theory. The instrument makes the theory correctable, and a theory that cannot be corrected is not really a theory. It is a very sophisticated opinion. So on this account, the breakthrough we are waiting for is not an equation. It never was. It is an instrument. And the reason nobody recognized it is that it did not arrive looking like one. It arrived as a satellite for encrypting bank transfers, which happens to maintain quantum entanglement across 1,000 kilometers at an altitude where spacetime is measurably curved. It arrived as a clock built to keep the world's financial exchanges in step, which happens to resolve the bending of time across a single millimeter. It arrived as a bead of glass levitated for a materials experiment, and a magnetic particle held above a superconductor to measure 30 attonewtons of pull, and a cloud of atoms cooled below 0.5 billionth of a degree because somebody wanted to know what would happen. None of it was built for this. All of it was built for something else, by people in different fields, who mostly do not attend each other's conferences. Every component of an experimental program for quantum gravity is now on a shelf somewhere. The assembly has not happened. That is a strange and rather hopeful situation to be in, when you think about it. The usual reason a scientific question stays open is that the thing you need does not exist and nobody knows how to make it. That is a hard problem, and sometimes it takes centuries. This is a different kind of problem. The pieces exist, they are made, they are working, right now, in 6 countries, doing other jobs perfectly well. What is missing is not an invention. It is a conversation between communities who have no particular reason to talk to each other, and a decision by somebody with funding that the question is worth the redirection. And that is where this stops being a story about physics and becomes something harder. Because I have to tell you about a man in Padua, in 1610, who would not put his eye to a tube. I told you that story at the start as though the lesson were obvious, and I want to take that back now, because the lesson is not obvious at all. Cremonini was not stupid. He had a coherent philosophical position, a legitimate complaint about the hardware, and a professional life built inside a framework that was still, in most respects, working. From where he stood, declining to look, was the rigorous choice. It was not until much later that it became the famous mistake. And now there is a laboratory, this year, where the most precise instrument ever built has walked directly into the gap between our two best theories, and the people running it are getting a usable number out by taking the proper time at the center of the trap. That is a patch. They know it is a patch. They have a deliverable and a deadline and a specification to meet, and the patch lets them meet it, and in their position, I would take it too. Nobody is refusing anything. That is the part I cannot put down. The refusal in Padua at least had the courtesy to be a decision. What is happening now is not a decision. It is 100 reasonable local choices made by careful people, none of whom is responsible for the fact that in aggregate the question does not get asked. There is no villain. The telescope is simply standing there, and everybody is busy. Which means the honest form of the question is not whether physicists are being foolish, it is this: how would you know? From inside, a refusal to look never feels like a refusal. It feels like rigor, or like good practice, or like having more pressing work. Cremonini did not experience himself as the man in the anecdote. He experienced himself as the careful one. Fuentes said something early on that I have not been able to shake. She said that at these scales we are blind, that we do not have a poor instrument, we do not even have our eyes. I want to retire that sentence now, because I do not think it is true anymore. And the change happened quietly, while everybody was watching the mathematics. We have eyes, small ones, not very good ones yet, pointed, at the moment, mostly at other things. But they exist, and they did not exist 25 years ago, and that is the first genuinely new fact about this problem in 110 years. So, is this the breakthrough in modern physics we have been waiting for? Not yet, and possibly not this particular version of it. But I think the thing we have been waiting for was never going to be a theory. I think it was always going to be an instrument. And the instrument is here, and what happens next depends entirely on whether anybody picks it up. There is one more thing I will pass on, and then set down, because she said it, and I do not want to hide it. Somewhere in the middle of describing all this, Fuentes remarked, almost in passing, that she suspects consciousness may be something missing from the equations. She offered it as intuition, not as result. There is no experiment attached to it, no prediction, nothing that could be shown to be wrong. So I am telling you she said it, and I am telling you that it does not currently belong to physics, and we are going to leave it exactly there. Because the more interesting thought, the one to fall asleep on, is much simpler than that. For 110 years, the deepest question we have, what is spacetime actually made of, and what happens to it when matter cannot make up its mind where to be, has been a question we could only think about. Not test, think about. And there is now a real possibility that within the lifetime of most people listening to this, somebody in an ordinary room with a cloud of atoms the width of a hair will get an answer back. Not a beautiful argument. An answer from the universe about something we were told we would never be able to ask. Thank you for spending this time with me tonight, and for coming this far into a question that does not have an ending yet. If this slow way of taking an idea apart is something you value, a like or a subscribe would mean a great deal. It is a small thing for you, and it helps me keep making these. And remember, the next time somebody tells you a thing can never be measured, that they are usually telling you about their instruments, not about the world. Good night, and may you never quite trust the word impossible in the same way again.